Good morning, professors. The general Pell's equation, x squared minus dy squared equals to n, to be called the Pell in short from now on, has fascinated numerous mathematicians for millennia, and research on various aspects of it is still very active. However, practical solvability criteria for the Pell, relying only on number-theoretic relations between the two parameters, d and n, appear to be rare in the literature. My paper, Solvability of the General Pell's Equation, Quadratic Reciprocity, and Real Quadratic Fields of Class Number 2, has produced two new results of this desirable kind through using tools from both classical and algebraic number theory. The central question is, for what combinations of natural number d and integer n will the Pell be solvable in integers? I have proved a necessary condition for the Pell to be solvable. I'm sorry, it's the wrong page. But I have proved a necessary condition for the Pell to be solvable, Theorem A, and a sufficient condition for it, Theorem B, which is a partial converse of Theorem A, conditioned only on concrete and necessary assumptions on D. The techniques used in formulating and proving these theorems include the quadratic residue, real quadratic fields, principality of ideals, etc. A few fundamental but handy properties of the Pell first. As far as solvability is concerned, assuming the coefficient d to be square-free won't lose any generality. My work fixed a square-free d and studied how the Pell with different n interact with each other. Second, once the Pell is solvable, denoted as condition Rn, the constant term n must be a quadratic residue modulo d. Third, lemma 3 is the well-known Brahma-Gupta's identity, which enables a multiplication operation on condition R. Namely, if both Rm and Rn hold, then so does Rmn. Fourth, I also proved lemma 4, which describes situations where a reduction operation on condition R can be performed. With a P satisfying these relations with D, if Rn holds, then so does Rn over P squared. Particularly important in my work is the consideration of this special modulus set M, which consists of the moduli, for which D is a quadratic residue. Bearing lemmas 3 and 4 in mind, I shall now start with a solvable Pell to deduce two necessary conditions to be called conditions P and Q, forming my first main result Theorem A. Recall that M is the special modulus set just defined. If n has a prime factor P out of M and of odd order, then reducing Rn repeatedly via lemma 4b will eventually contradict that P has odd order, forming a contradiction. Thus, the order must be even. I call this result condition Pn. Starting over again, the common prime factors of n and d can be used to construct this multiple of n. Given Rn and as Rp squared minus d holds trivially for each p, by lemma 3, R of this multiple holds as well. Rearranging it as this right-hand side, then one can drop the purple part using lemma 4a, leaving only the green part Cn of which R holds. Then Cn will be a quadratic residue, modulo d, and I call this result condition Qn. I have just proved that Theorem A that R implies P and Q, where P is a parity condition on the orders of prime factors of n, modulo which D is a quadratic non-residue, while Q is a quadratic reciprocity condition on Cn modulo D. For C, defined in definition 1, an important property is that while n may not be coprime to D, Cn must be, as I proved in lemma 2. In the reverse direction, my major result, namely Theorem B, as a conditional converse of Theorem A, ensures that P and Q will imply R, provided that D satisfies these requirements. D is congruent to D, the real quadratic field Q with D has class number 2. D is congruent to 2 or 3 modulo 4. And either R negative 1 holds, that is, the negative Pell is solvable, or Q negative 1 does not hold, that is, negative 1 is a quadratic non-residue modulo D. For the rest of my presentation, I will explain the necessities of requiring the above in D in Theorem B, then outline my proof, followed by giving the main steps of my proof. First, why Q root D with D congruent to 2 or 3 modulo 4? Because, in this case, its ring of algebraic integers will simply be Z root D, in which the norm formula for principal ideals matches the absolute value of the left side of the Pell. Moreover, why class number 2? Whether Q root D has class number 1 has already been known equivalent to the solvability of certain cases of the Pell. For higher class numbers, I have found counterexamples to Theorem B's assertion that P and Q implies R. And when an algebraic number field has class number 2, the principality of ideals enjoys these nice properties as in lemma 6, opening up an algebraic approach to study the Pell. Finally, why assume R-1 is true or Q-1 is false? A superficial reason is that, if not, with the trivial P-1, Theorem B's assertion would fail already in the case of n equals to -1. The deeper reason is that, with such assumption, I managed to obtain key lemmas 31 and 34, which will eventually bridge the largest gap in proving Theorem B. These two lemmas are slightly weaker versions of Theorem B. With identical setting as Theorem B, plus that n is in M and is coprime to D, Pn and Qn will imply the weaker solvability condition R plus or minus n, which only requires at least one of Rn and R-n to hold. More importantly, R plus or minus n can be translated into algebraic terms. Given any n in the special modulus set M and any k-square congruent to D modulo n, I constructed an ideal generated by n and k plus square root d, as in definition 16. Via 10 meticulous lemmas 17 to 27, I proved that they actually belong to the same ideal class In in Z root D, and that the principality of this ideal class In is indeed equivalent to R plus or minus n. First, we have successfully translated R plus or minus n into algebraic number theory terms. Here is my outline of my proof of Theorem B. Starting from Pn and Qn, we will modify n in multiple steps until P and Q will imply R plus or minus here. They include applying the previous modifications C once, and this technical removal of square factors twice. After getting R plus or minus here, we will undo all these actions, obtaining purely R plus or minus n. The last step towards the ultimate Rn will then require only simple logical arguments. Here are the concrete steps. Firstly, I proved lemma 14 to extend the ideas of multiplication and reduction to P, Q, and R, as shown here. It provides these 4 steps, which involve adding S to P and Q here, or removing S from R plus or minus here. The next step is to deal with C. Therefore, we proved the property that C preserves P, Q, and R plus or minus in lemma 28, as shown here. In order to apply lemma 28c, which requires n in M, I also proved this crucial relation among P, S, and M in lemma 22. Bridging the gap are the aforementioned weaker versions they provide these 2 steps, remaining only the largest gap of P and Q implies R plus or minus to overcome. Bridging the gap are the aforementioned weaker versions of Theorem B, as shown here again. Aided by this basic coprimality property of C, as in lemma 2, this step is then completed. We started from Pn and Qn, and we have just got R plus or minus n. Then why must Rn be the only possible outcome in the n as Theorem B requires? Just suppose that Rn is false, then R-n must be true, which implies Q-n by Theorem A. Q has the property that if Q-n and Qn are true, then as proved in lemma 13, so must Q-1. With Q-1 true, we are then forced to pick the other case R-1 true out of this compound assumption. Finally, using lemma 3 to multiply R-1 with R-n, we will obtain Rn, and we are thus done. In summary, I have defined conditions P, Q, and R in connection with the solvability of the Pell. I have proved that the solvability condition R, our main goal, is closely related to these simple number theoretic conditions P and Q about D and N. To be precise, R always implies P and Q, as proved in Theorem A. And under these concrete and necessary assumptions on D, the converse, P and Q together imply R, also holds as proved in Theorem B. That concludes my presentation. Thank you.